Now I will tell you about semantic data integration in the SmartEdge project and how do we approach this issue that Felipe just described in the project, and what do we do in terms of tools to do semantic integration in SmartEdge. So here we have three different components. So this is the technical work that we are doing together with Chevriel and Hesso and other partners in our work package for semantic integration tools. And there are three levels where we get the data, where we try to harmonize the data. So first of all, we have our various use cases. You learned about them yesterday. We have different devices from different domains. They're using different data models there. So it comes from automotive domain, there is manufacturing, there is healthcare. So first of all, we need to get all the data and try to unify it on the level of communication protocol or above the communication protocols that these devices are using. Then when we got this at the second level, second from bottom, we provide a data ops toolbox for continuous semantic integration. That means bring all data models together, harmonize them on that level so that we have the common understanding what this data means. And when this is done, we can do the low-code approach for programming recipes. This is what I've been showing in the previous presentation. But the idea is that if you know where to find your capabilities, skills of your device, how they look like, how to trigger them, then you can create kind of the templates of your applications that you want to execute, the recipes, and then bring it back to the devices, connect with them, and execute your recipe. This is the architecture picture, also simplified for the SmartEdge on the device level, also starting from bottom to the top. We have different devices. They speak different communication protocols, being it OPC-UA, MQTT, DDS. We have Bluetooth Low Energy, whatsoever. This is the point where we need to harmonize it on the communication protocol level. Then when we get this data, we can do some magic to put it in a knowledge graph to convert it to the same model. And then on top, we can use any low-code programming tools. So for us in the work package, it would be Mendix. There we create recipes, create any applications that can be executed on any of these devices underneath. Our work is concentrated around these 5 topics: the concept of continuous semantic integration, then finding the generic semantic modeling for the project, so across all the use cases. And then 3 last points that I will be concentrating on today are the standardized semantic interfaces, the concept of data ops toolbox, and the low-code approach for orchestration of the apps. So the data ops tools will be the central piece, but I will also touch the semantic interfaces and the low-code again. So let's start with the interfaces. This is more or less the picture that we have right now. So we have devices coming from our use cases. It can be industrial POCs, it can be AMR, it can be a traffic node, it can be any IoT health device like sensors from Hesso or IMC or anything else. They speak different communication protocols, and for all devices that do not speak OPC-UA, we envision to set up a middleware that will harmonize the communication protocol for it. So at this place, So the middleware, for now, we want to use Zeno at this place, and that will bring MQTT and DDS messages in the same kind of middleware structure, so that you can access from the northbound, you can access this data via the REST API, no matter what is on the southbound. For OPC-UA, we could also go this way. So Zeno actually has OPC-UA bridge as well, but if you heard my talk yesterday, we use OPC-UA also as information modeling tool. So at this place, if we directly plug it into the middleware, we will have the communication part, but we will lose the information modeling part. That's why our use case on the left with the industrial POCs using OPC-UA is not matched to this middleware stuff. It directly goes to the interoperability level where we put the information modeling. And on this level, on the level of interoperability highlighted in yellow on the slide, we also have different things. So in Smart Factory Siemens use case, we use OPC-UA information modeling to model the data, to bring meaning to it, to bring semantics to it. It can be FX, which stands for field level exchange. It can be any other information model. And for all the other use cases, we want to use Web of Things thing description to describe the interfaces of the devices and how to access them. Then on top, to give more meaning to the data that we get from the devices, we use different ontologies, so coming from the domain. So this is domain level ontology, robotics, smart traffic, healthcare, again, manufacturing, OPC-UA companion specifications. And when we pump all this data together, we can create recipes based on the capabilities that would be defined in these use case data models, together with the information from Web of Things thing description or OPC-UA, how to access this data on the device, really. And this is the place where we merge the capabilities with the real devices, and we can execute them in order to run the applications. Yeah, this is the bit about low-code programming in Mendix, and I showed you yesterday a bit, and it will also come in the next slides. About bringing Web of Things, thing description, and OPC-UA information model together in one knowledge graph. So for things description, we have this toolchain where we use a Python-based repository for thing descriptions that already exposes a Sparkle endpoint that we can use. So this is an open source library that we use for that Web of Things part of our use cases. And for OPC-UA information models, we envision to use Chimera framework. I will tell more about this in the next part. So this is our tool for data ops, for semantic management of things. And at the end of the day, we could bring both data models from Web of Things and from OPC-UA information models in the same knowledge graph, where we will store the devices and their capabilities, what their skills are. So now about the data ops tools, which should do exactly this and also can do more. So the data ops provides the infrastructure for integration of different things and their applications. It sits on top of the standardized semantic interfaces. And it has a declarative approach to define the mappings, so how you convert the data that device is giving you to the to one model, the SmartEdge model. And continuity, so this continuous semantic integration, there are also two bits here. So we can use this tool first to, at the design time, so to say, to convert the models that we have into into the knowledge graph, or we can also do it on the fly. So when we know that one device speaks, awaits data model A, and another device gives you a data model modeled in B, then we can on the fly convert one data model to another data model so that we don't need to change it on the device level. This implementation can run both on the cloud environment, but also can run on the edge devices for this runtime conversion, for example, and will be integrated with the low-code programming tools. So whenever there is a need to convert one message to another message, then we can call it from Mendix runtime and do this conversion on the fly. How does it look like? So here we use so-called any-to-one mapping approach. As said, we have different standards, different data models from different devices and various domains. And we convert all of them, so we define the mapping to convert all these formats to one model in the knowledge graph. So for each system, we need to create kind of mapping, how the data that is modeled in one device should be converted to this data model in the knowledge graph. As a outcome, we get this interoperable knowledge graph where we have all our devices, their capabilities represented in the same form. We can query, we can search for the skills, and we can also use it for matchmaking purposes whatsoever. Assumption is that there is a common reference semantic model that supports the definition of all the mappings, so that we know what is the outcome of this conversion process. How conversion looks like. There is a so-called lifting process and lowering process. So on the one hand side, we have a device A that speaks standards A, and first of all, we lift it to RDF, so from any data model to RDF. This is what we had on the previous slide. And then whenever we want to access the knowledge, we can lower it to the standard B. Again, we need to know what is the logic of this lowering mechanism. We also need to have a mapping to do this lowering from RDF to B. And in both ways, we need to know how we go this way or another way. Again, the idea is that there is no single interoperability problem. You have various protocols, you have legacy devices, you have greenfield devices. Like in this vision, you want that all of them work together, but there is no single interoperability solution. So basically, you need to write these mappings for each and every device that you have, for each and every data model. For that, Chefreal developed the Chimera framework that does exactly this. Lifting, lowering, and in between you have the RDF graph operations, so that you can run Sparkle queries on the graph, on the resulted RDF graph. I will show this bit in my demo later, but I also wanted to show you again the low-code programming part, creation of the low-code applications and orchestration. This is the part that comes from Hesso, and here again, if you were here yesterday, then that was the part about Mendix. The idea is that we will have a recipe, so-called template for the applications that we can run then on the swarm. We use the capabilities, the skills of devices to define a recipe, and then when a recipe is complete, then we match a recipe that we want to run with existing devices that are there, that are ready to join a swarm with their skills, and so we create an application that at the end of the day we run on a swarm. So again, in our use case, we do it in the design time. David would do it in the runtime, but the idea should be the same. Matching is done on different levels. You can match the inputs and outputs that are required by a recipe. You can match the interfaces that are required. But again, if you have middleware, then you don't care about interface so much. You can always use Zeno to collect the data and to trigger any actions. We use the semantics coming from the knowledge graph to get the information about existing skills in the system, to discover them, and also to find what devices are there and if it's enough to execute the recipe that we have just designed. And then Mendix is also there to orchestrate and monitor the running applications. This is how we run it at the end. This is how Mendix look like. So these are BPMN activity diagram, sequence diagram. So you have always the input parameters, which might be required capabilities. Then you define the business logic, what should happen. You chain the skills that you want to run, and then you do some data processing in between. So what should happen if. So, and now the demo time again. What I want to show you is this bit about data lifting in this case. So I will not do the lowering because what I want to achieve is more or less the same use case as I showed in my previous presentation. So I have an OPC-UA server that is described by OPC-UA information model for robotics, and I want to find out which OPC-UA nodes I need to use in order to control the position of my robot. To do that, I will grab the information model of my OPC-UA server, throw it at Chimera. Chimera will lift it to an RDF graph, and then with the RDF graph that I will get from it, I can run a SPARQL query to find the right nodes. So this time without a chat, this time I will just do it manually, but let's see how it works. So you now should see my screen, right? Yep. So Chimera is now part of our integration environment. So this is running on Dell's premises, and we can just use it. So for my demonstration, I would need to copy the node set file of the server of a robot that I'm using and give it to Chimera in order to create an RDF graph out of it. So let's try to do this one. So again, there is already an implemented mapping so that Chimera knows how OPC-UA node sets look like, how to convert it to a knowledge graph, and this is already running there. If you have a new data model, if you have a new protocol, you would need to first create this declarative mapping to do this. So now it says it's created. One tiny thing, I would need my model URI to get the RDF graph. And then what I can do is to ask Chimera to give me back the TTL. In the meantime, we got the TTL file. So this is the knowledge graph representing the model that I put there. And now I can use it in order to run my SPARQL queries to find the node ID in OPC-UA namespace that I was been looking for. I already copied this graph to GraphDB, and I hope it should be here. Let's just try and fire a query here. So if you remember the server model that I was showing you yesterday, there were several robots modeled in OPC-UA, and all of them had different number of access, and we were looking for a node ID to control an actual position of one of the robots. So now if this all works, then we will get the access of all the graphs, which has current position and the node IDs that corresponds to it. So there is an XYZ axis of one robot, XY axis of another one, and one 6-axis robot, which is other one. This is the node that I was controlling yesterday, showing you the example in Industrial Metaverse. So this is the one from the Nuremberg lab. The others are the other robots. So this is how you can use it in order to lift the OPC-UA information models, and then to run. To use the knowledge graph in order to find the right information, and later you can use these node IDs in order to create your recipes and your applications. Again, on top, as I showed you yesterday, we can put the chat interface, not so to automate this step here. If the chat model, if the large language model is capable of generating this Paco interface, and sometimes it is, then we can also automate this step.